Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And within that playlist, I'm creating little mini-series depending upon what experimental design we're using. And this is part 3 of a little mini-series on analysis of covariance. And here we're going to look at deriving the least squares estimates for the unknown parameters. So I'm going to give 3 reminders and then jump into the actual derivation of the least squares estimates. So the reminder 1, we talk about the normal equations, and I actually don't know why they're called the normal equations, but they are. And I'm going to say see video that I have on multiple linear regression, least squares estimates, where we actually derive these normal equations. So we have a linear model, we look at the sum of squared errors, take the partial with respect to beta, set it equal to 0, and then what's left over, the normal equation. And so what's magical about this is we're trying to solve for these unknown parameters, but the matrix out front may or may not be invertible. And in the analysis of variance world arena, it's often not invertible. Okay, that's reminder A. Reminder B is I'm going to point you back to the 4th video in this big playlist, General Linear Models Design of Experiments, where we looked at the least squares estimator of beta. And we have our general model, and the column space is not full, it's not full rank or full column space. And the least squares estimate has to satisfy this equation. It's x beta tilde, where this is the least squares estimate for beta, my, where m is the perpendicular projection matrix on the column space of x, and it's defined this way. And that's the generalized inverse operator. Now, reminder number C, or the 3rd one, is if we have a model, but it can be partitioned into this. So the x, we have x1 and x2, and the beta is partitioned into beta 1 and beta 2. But the column spaces of x1 and x2 are orthogonal. That means that we can actually just do the regression of y, x1, beta 1, epsilon, and then we could do separately y and then this one. We can just do them independent of each other because they're orthogonal. And because we're doing them independent of each other, then property B, or reminder B, applies, that it has to satisfy this requirement. Okay, so 2 ANOVA designs here. So parts 1 and 2 of this little mini series, we look at model development, and then we look at the column spaces of the design matrix, and we ended up with this. So y is equal to x delta I minus mx, where this is the perpendicular projection matrix onto this column space x, z gamma. Z are the covariates in our analysis of variance. And if we sort of unmatrix multiply it, we get to this setting. But in part 2, we notice that x and I minus mxz are orthogonal. So we can think about them as 2 separate or independent linear regressions, to find the least squares estimates. Now, we have y equal this, x in quotes, and then this unknown parameter plus epsilon. So we are in this setting right here. So we write down the normal equations, and that's what we get here. So this is x transpose x, the unknown parameter, x transpose y. So these are the normal equations. And then let's multiply this out, and we get this equation. Now notice that when we do this multiplication, we get, that this times that is equal to that, and then this times that is equal to this. And so in a sense, we're doing them, that's what we get here, right? And then this second piece, we multiply it out and we get this. Now, if this matrix is invertible in the front, we can multiply, or whether it is or isn't, we can take it to the other side with the generalized inverse matrix. And I have a video called Generalized Inverse Matrices in my matrix playlist. Very informative, by the way. And so this is it. This is the least squares estimate for gamma, which are the parameters associated with the covariance. Now, if this is invertible, then gamma is uniquely estimable. If it's not, then there's an infinite number of least squares estimates. In the R software program that we do, we pick an example where this is invertible, and then this ends up being unique. Now, from parts B and C, we know that this piece, so, and they're independent, must satisfy this, right? This is the least squares estimate for delta. This is the perpendicular projection matrix on that column space of X. So part B says it satisfies this. Now, here is the model that we're looking at. But this piece here originally was this, X beta MXZ delta gamma. Right? And actually, when you multiply this into here, it cancels with this. We added a well-chosen zero initially. So, this piece and this piece subtract off, and we're left with this. And the least squares estimates must satisfy this equation. Now, if we take this to the other side, and of course switch the order, so this is here, that's there, and that's subtracted over, we get this. This piece right here, by part reminder B, is this. And if we left factor out mx, the perpendicular projection matrix on column space of X, we're left with this. And so this is it. So the least squares estimate for beta must satisfy this equation. Now, we could put in what the perpendicular or the least squares estimate of gamma is, and that's what we do here. And we're going to make use of this in the R software illustration of this. It's actually pretty cool. We're going to come up with a few different least squares estimates, and they're all different. But when we pre-multiply it by X, then it's uniquely the same. It's pretty cool how that all works. Okay, so that's all we have for this video. Next, we're going to look at the sum of squares, errors, and f-tests associated with these unknown parameters. Hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.